Simon Levin, professor of ecology and evolutionary biology at Princeton. And today it's my pleasure to introduce one of our star students who's been leading a lot of the work here. Chadi Saad-Roy got his undergraduate degree at the University of Victoria, working with Pauline Vanden Dries and Junling Ma. And he has a strong mathematics background, but he's also gotten very deep, as you'll see, into the dynamics of infectious diseases. We began working together on influenza, and indeed this was two plus years ago, began thinking about the evolution of asymptomatic infections and how wouldn't that be a good idea for the virus. Unfortunately, the virus seems to have read our papers, and shortly after we got started, even before we published, as we all know, SARS-CoV-2 developed this asymptomatic phase. But since then, Chadi has worked on a wide variety of problems, including the evolution of asymptomatic infections, optimal dosing regimes, the future of SARS-CoV-2, and a number of other problems that he will tell us a bit about. So today, Chadi's going to lead this discussion about SARS-CoV-2, and I'm looking forward to hearing how he puts it all together.
Thanks very much for the introduction. It's very kind and very happy to be here. Thanks, Madhav and everyone for the invitation. So today I'll provide a very brief overview of some of the work we've done on SARS-CoV-2 immune dynamics and immune-epidemiological outcomes. So this is very simple models, but we learned something from them. So obviously, as everyone knows, there's not much of an introduction needed to introduce SARS-CoV-2, as we're currently living through the pandemic. But there are a number of unknowns that surround immunity after vaccination or recovery from infection. So early on, it was more about the unknowns surrounding infection. And now, obviously, since especially in the US and other countries with widespread vaccination, now the question is, what's the duration and the strength of immunity following vaccination? So obviously, trying to untangle these is going to be important as the pandemic progresses to inform different types of mitigation strategies as we go on. So obviously, I don't think I need to say this, but I did put in the slides that models are useful here. The first thing I just want to touch upon, which I won't go into too much detail, but is the setting where you have low constant infection levels in vaccination and potentially a seasonal switch. So what happens when you have this kind of setting? Well, turns out if you have the seasonal switch, pre-existing immunity settings with constant infection levels, the math really works out very nicely. And you can determine conditions, basically relations between individual and community immunity under all these different circumstances. And so we published this in Interface. If anyone's interested in reading these, I won't go into the detail of all the relations, but it is it's neat how the math works out. So obviously this is omitting any epidemiological dynamics here. We're just assuming constant influx of infections. But as we know, epidemiological dynamics are very important, especially as we shape policy. So how can we model these? The classical SIR models will assume either lifelong immunity or return to complete susceptibility. That's going to be known as the SIR or the SIRS model, right? We can tell that an individual who's been infected once and who might lose immunity doesn't go back to complete susceptibility. There might be some buffering. So we need a different kind of model. And so that's what we've examined this in this paper that I'll describe very briefly. So this is this SIR bracket S model framework. In a nutshell, this is the model diagram in the middle here. And there's 5 different kinds of individuals. There's the fully susceptible individuals, the individuals with a primary infection, the fully immune individuals, the partially susceptible, and the secondary infections. And basically you can look at the flow here, and we don't have to go through all the parameters, but there are a few parameters that I would like to point out. So the key parameters here are this alpha, which is the reduction in infectiousness of a secondary infection. And perhaps the most important parameter is this epsilon, which is the reduction in susceptibility to a secondary infection. Delta is, so 1 over delta is the average duration of the R class. And so on the one extreme, you've got the SIR model. And on the other extreme, you've got the SIRS model. And somewhere in the middle, you've got this, basically you can interpolate continuously between both models. This model then allows us to probe the uncertainties surrounding immunity, depending upon the values of epsilon and delta, et cetera. If we do this, we can look at the confluence of non-pharmaceutical interventions, seasonality, and the strength of immunity, which this is epsilon, the strength of immunity, this reduction in susceptibility to a secondary infection. And here, we're looking at three different scenarios of non-pharmaceutical interventions. And the key message is these are busy plots, but each line, for each value of epsilon, there are two lines, a dotted, which is the secondary infections, and the solid, which is the primary infection. And this is for 5 years. And the solid part is where you've got the non-pharmaceutical intervention on, and the light is when it's not. And so the key message here is that you can actually get some unintuitive effects when you've got seasonality in non-pharmaceutical interventions and the strength of immunity varying. For example, you might actually end up with a delayed second peak that might actually be bigger if you've got stronger immunity. So this is somewhat intuitive and just is due to dynamical resonance in the seasonal cycle. So obviously, as you can tell already, this is pretty complicated, and there are a number of different dynamics that can emerge just from simply varying this epsilon parameter. So it's obviously a very important parameter to quantify. If we incorporate vaccination, this is pre-vaccination era. And so we just incorporated it very simply by considering a single class. So basically you've got this vaccinated class now, and individuals from the susceptible class get vaccinated at a certain rate, and then the vaccine immunity wanes at a different rate. And then we just assume that once the vaccine or the natural immunity wanes, they go to the same class. And so now we've got one extra compartment. Now with this model, still analytically tractable, and we can prove that there's a unique endemic equilibrium if the associated reproduction number is greater than 1. Otherwise, there's only the disease-free equilibrium. And then we can get an analytical expression for the minimum vaccination rate required for eradication. And so I would encourage the interested listener to go and look at the supplement if they're interested in this. And basically, then we can plot these equilibrium values as functions of the vaccination rate for different durations of immunity and different susceptibility to secondary infections. Basically, this is, we see here the fraction of population infected at equilibrium, and obviously, as the duration of immunity gets bigger, this goes down, and as the susceptibility to secondary infection gets bigger, this also decreases. And then on the other panel, we've got this proportion of susceptibles that are vaccinated daily on the y-axis, and on the x-axis is the susceptibility to secondary infection, this parameter epsilon. What I find very interesting is that for low values of epsilon, this minimum vaccination rate is almost independent, basically, to the duration of vaccinal immunity. Now, as epsilon gets big, all of a sudden, the duration of the vaccinal immunity does make a difference on this minimum vaccination rate needed. So there's some interesting interplay between the susceptibility to secondary infection and the duration of vaccinal immunity required to reach eradication. So then we can project in the synoptic medium-term landscapes and look at different situations, different scenarios for what we might see over the next 5 years. Here are some area plots. So on the top panels, we've got the severe cases. We just make some assumptions upon how many severe cases there are of primary and secondary infections. And on this panel here, it's an area plot, which shows the fractions of each individual in each compartment, depending upon the types of infections. And so on the top, we've got without vaccine. So we've got poor immunity, robust immunity. So we can see that with poor immunity, it cycles rather frequently. And with robust immunity, you basically can reduce infection levels and then comes back after quite a while. With vaccine and poor immunity, you still decrease the infection levels, decrease the severe cases, but it might persist. And then with robust immunity and vaccine, you can really knock it down. So that's kind of interesting and shows a broad variety, basically just on a few parameters. You change a few parameters and the potential outcomes change drastically. Based on this, we can see that it's very important to quantify these parameters and to try to understand what the immune landscapes are as we progress through the pandemic. Now, obviously, we're assuming a well-mixed population in all of this, but there can be other situations where we have a group of individuals that are vaccine hesitant and choose not to get vaccinated. And so we can incorporate this simply in this model by just considering another group that chooses to not get vaccinated. And now we can do similar analogous calculations where we look at the proportion of vaccine adopting susceptibles that are vaccinated daily as a function of the fraction of population that refuses vaccines for three different scenarios where they're mixing homogeneously, where there's increased transmission associated with vaccine refusers, and where there's decreased transmission associated with vaccine refusers. And here again, you see that as this fraction of population that refuses vaccine increases, the duration of immunity becomes more important, especially in the setting where this susceptibility to secondary infection is low. And we also see that it's actually good to decrease transmission if individuals refuse vaccine, and then the proportion of vaccine adopting susceptibles to be vaccinated increases less rapidly. And then down here, we can actually then compute the fraction of individuals that refuse vaccines so that R naught less than 1 cannot be achieved by vaccination alone as a function of the relative contact rate. So you can see this kind of gives you some type of indication for when you may end up with eradication or not. Refusers with higher transmissions make it much harder to control the disease via vaccination. And there's interesting interplays between the strength and the duration of immunities that it's good to, again, highlighting the importance of determining what these parameters are. And so now we can take this expanded model and examine the synoptic landscape and how vaccine hesitancy may change the synoptic landscape. So here's, again, 4 area plots. And again, we're looking at long and strong immunity, short and weak immunity. And then on the top row is homogeneous mixing. And on the bottom row, we have increased transmission associated with refusers. And so you can see that this vaccine refusal can actually impact the dynamics quite severely over the span of 5 years. And there are a number of additional considerations. Some things that we've looked at as well in the supplements are this heterogeneities in transmission and immunity. So this is the flow diagram for it. Don't have time to go into all the detail, but if one's interested, I would encourage them to look at the supplement here. Pulse vaccination or different seasonal patterns. And we have this online interactive application where individuals can play around with the different parameters and try to look at the synoptic landscape for whatever parameter they want. So the idea is as there's more and more data, as we accrue more information, we can refine these predictions. So this is, again, a very simple model giving us some pretty interesting insights into the potential dynamics. Now, as we progress into the pandemic, well, we figured out that some vaccines are 2 doses. And then a number of questions arose as to whether we should change the gap spacing between the doses or not, and what might be the consequences of this. And so these consequences can be epidemiological or evolutionary. And so in a follow-up paper, we examined these using an extension of this model. So I'll briefly cover some aspects of this paper now. Obviously, the previous model just had 1 compartment for the vaccinated individual. So we have to refine this. And so the way we do this is we actually incorporate individuals with 1 dose, individuals with 2 doses, and then each of these has their own waned 1-dose immunity, waned 2-dose immunity compartments, and then infections after these. And then the rest follows as before. So the primary infections, the recovered, the secondary susceptibles, and then the secondary infections. And so with this extended model, you can already see that the complexity increases tremendously just by adding in this seemingly simple addition. Now we have a number of classes, and as you can tell down here, a number of individuals. So the potential different types of individuals in the population are actually quite diverse now. And so I'll just draw attention to a few parameters. There are a lot here, but basically what I want to focus on is this omega here. So 1 over omega is the average time between the 2 doses, this interdose period. And then we're going to couple this to the vaccination rate somehow. So we're going to look at a function somehow like this. So basically, first dose administration rate is going to depend upon the average interdose period. So if you have a longer interdose period, you can administer more first doses. And if you have shorter, then there's less. Then we can use this model. Now we have number of epsilons, right? So before we had 1 epsilon for this reduction in susceptibility to secondary infections. Now we've got epsilon 1, epsilon 2, epsilon V1, epsilon V2, and then a regular epsilon. So there are a number of uncertainties now. And again, these models are simple. Well, this one's more complicated than the previous ones, but we can still examine across a range of parameter values what are the different potential outcomes. So I won't go through all of the different possibilities, but I just wanted to show a few. So for example, here we've got less robust natural and vaccinal immunity. And here we've got shorter and weaker immunity following 1-dose vaccination on the top row. And then the bottom row is longer and stronger immunity following 1-dose vaccination. And then the columns are different strategies. So 1-dose, 24-week interdose, 12-week interdose, and then the recommended 2-dose strategy. The top is just a schematic of the proportion of individuals that are vaccinated. Then we've got the cases in red, the severe cases, again, with some assumptions upon the fractions of infections that are severe in black. And then we've got the area plots with all the different kinds of individuals laid out here, coloring, making up the population. So as we can tell here, if you've got short and weak immunity following 1-dose, a 1-dose strategy may be good in the short term, but then lead to bigger outbreaks later on. compared to like the recommended 2-dose strategy. If you've got longer and stronger immunity following 1 dose, then obviously this is the strategy to go. It mitigates cases in the short and long term. So evidently, this is again just one half of a panel really that we're looking at, but it just illustrates that there are a number of different possibilities. And obviously, you can see that a lot of the potential negative outcomes associated with a 1-dose strategy can be mitigated by doing a 12-week or 24-week interdose period. So just basically ensuring that individuals get their second dose eventually. So there are a few different key points to take away from this, but it just kind of highlights that these are important parameters to determine as we go on forward. And so this is, again, just epidemiological outcomes. So now there's a number of other things that we can look at, such as cumulative cases across the medium term, and as well as this minimum first dose administration rate. And again, we can compute this based on the R0 and figuring out what you need in order to get R0 less than 1. And so again, this is severe cases and total cases. And so the interdose period is on the y-axis and the 1 to 2 dose immune response ratio is on the x-axis. And you can see that depending upon where you lie on the surface, you're going to end up with different outcomes. And then the minimum first dose administration rate, you've got this epsilon 1 and epsilon 2. And then as you increase the gap between the two doses, then you end up with more of a dependence on epsilon 1. You can see that it's important to try to determine what epsilon 1 is and what epsilon 2 is to then kind of infer what situation you're in and to decide what's an appropriate recommendation. So then, of course, we turn to this evolutionary scenarios. And so to do this, we couple a simple model based on Grenfell et al. 2004, which is basically based on like a within host evolutionary model. And we look at 3 different scenarios. So basically, we've got the potential net viral adaptation rate as a function of the immune pressure. And that's going to depend upon the strength of selection and the viral abundance. So this parabola is just illustrating where this potential net viral adaptation may be. So each infection type is going to lie somewhere along this curve. And so we look at 3 scenarios. One where there's low potential viral adaptation in all 3 classes, one where there's low potential for natural or 2-dose immunity, and then high with 1-dose immunity, and one where all 3 are relatively high. So the whole point of these models is that we're able to examine a range of outcomes to then inform what may or may not happen depending upon which scenario we're in. So if we look at these different outcomes, and again, not looking at all the different possibilities, but just examining one, you can then look at different strategies. So here we've got the 1-dose strategy, and these are the 3 different evolutionary scenarios. We've got 24-week interdose period and the recommended 2-dose strategy. And then below, we just present the infections after waned immunity and then the partially susceptible individuals. And you can see that depending upon what scenario you're in, the potential viral adaptation rate is going to be quite different. And so obviously, if you're in the scenario 1 where there's low potential in all 3, then your dosing strategy doesn't really matter. It doesn't really affect the evolutionary outcomes. This is just a very brief overview into this. So there are a number of additional considerations: switching dosing strategies, ramping up vaccination, different vaccination rates, or vaccine refusal, or vaccinating a subset of the population. So again, if someone's interested, you can look at the supplement and the interactive online application to try to get a feel for how these models work and what are the driving parameters. I think the next big question was, what happens when you have vaccine nationalism? So now you've got a lot of abundance of vaccine, and some countries decide to hoard the vaccines and not share them. So what might happen with this? So this is the next work we've done, examining this. So again, we're just extending the previous models that I've done before and looking at 2 countries. So basically, we've got this coupled model where we've got immigration, and a decoupled model where we've got no immigration. They're always coupled through vaccine sharing though, right? So there's a fixed vaccination rate, then it splits between the high access region and the low access region. And in the coupled model, we also allow for potential transmission increases. Looking again right now at the transmission decoupled model, the long-term equilibrium, we can kind of get a feel for how the different parameters interact. So if we look at this panel here, and again, this is just one example, but assuming we have some type of baseline transmission, and then we look at the poor immunity, intermediate immunity, good immunity, and robust immunity. And then we look at the symmetric, less transmission in high axis region and less transmission in low axis region. And we're just looking at the total number of infections, so primary plus secondary. And as you see, this is the average infections at equilibrium across both countries as a function of the fraction of vaccine allocated from the high axis region to the low axis region. So by far and large, it's important to share vaccines, especially as you can tell, the colors are different global vaccination rates. So you can see that no matter what situation you're in, obviously, if it's symmetric, then it's just symmetrical on both sides. But if transmission isn't symmetric, then there are a number of complexities that arise. But basically, by far and large, it's very advantageous to share vaccines to decrease total infection levels. Now, I think what's very informative is to look at one of these plots. So this is just basically the average across both countries, but let's look at within one country. And so this is for a fairly low global vaccination rate. And we've got the high axis region in solid and the low axis region dotted, and the equilibrium infections on the Y, and then the fraction allocated on the X. And you can tell here that when the global vaccination rate is low, then basically higher allocation of vaccines from the high axis region to the low axis region increases the number of cases in the high axis region and then decreases the number of cases in the low axis region. So there is a seeming small trade-off. Now, when you increase the global vaccination rate, however, this disappears. And all of a sudden, you can tell that it's advantageous to share a lot of vaccine for both countries. So it doesn't affect the high axis region as you share more vaccines, and the low axis region just decreases the number of infections. So this really stresses the importance of increasing global vaccination rates. So this is the long-term equilibrium. We can also look at the medium-term outcomes. And again, looking at, this is going to be a very busy plot, but just to illustrate some points. So now we're looking at, again, it's very analogous to what I've shown previously, but we've got all these different compartments of the two-dose model, and we can look at the different dosing policies and just assume that we've got an allocation scheme of no sharing or equal sharing, and then one dose policy and a switch to two-dose policy. Now we've got to split each panel into the high axis region and low axis region. You can see that by far and large, sharing vaccines is beneficial, will decrease cases across the strategies. And obviously, depending upon the specifics, there might be specific considerations, but this is just to illustrate the power of these models to try to generate some qualitative insights into what may happen. So this is again assuming that the two countries that the transmissions are decoupled. The only way that they're coupled right now is through this vaccine allocation. So now what happens if you couple them? Now we allow for coupling and transmission, so it's some immigration, and then we also allow for increases in transmission rates through some evolutionary events, so just potential transmission increases through PTIs. And so you can tell here, I'm not diving too deep into these plots, but you can see that there are a number of complexities that arise. So here's the immigration rate on this axis. And again, we always have this vaccine fraction retained by the high axis region on the x-axis. And then on this axis, it's the reproduction number ratio. And so you can tell that as the details, especially with regard to the transmission, which is basically this reproduction number ratio, depending upon the details of how these are, the different outcomes are slightly different. But by far and large, it's very advantageous to share vaccines in decreased cases and to basically mitigate potential evolutionary outcomes elsewhere. And so I think this is emphasized when we look at this panel here, where we look at the cases where we compare a coupled and decoupled model. And again, the coupled model allows for this potential transmission increase. So you can see that when you retain all the vaccines by the high axis region, then you end up with, in the decoupled model will predict fewer cases because you don't have this potential evolutionary outcomes that are occurring. And the coupled model now shows that, well, actually, retaining vaccines actually will be worse than what would have been predicted under a decoupled framework. And you can see here, there are no evolutionary outcomes, and now there are. So basically, this kind of gives general insight into the potential qualitative dynamics. And again, I omitted many different aspects, but you've got this, we could have overall higher transmission, we could have asymmetries in population sizes. We can further examine the evolutionary considerations of the vaccine allocation schemes with the vaccine dosing regimes. But to do all of this, I would encourage an interested listener to look at the papers and the supplements in the interactive online application to try to get a feel for how these parameters work together. So just to conclude, the strength of immunity is a central parameter. I hope I've convinced you of that in this talk. There's an interesting and important interplay between immunity, non-pharmaceutical interventions, and seasonality. There's a wide range of medium-term scenarios, depending on, and a lot of it crucially hinges on this robustness of immunity following infection or vaccination. There's equitable sharing, has epidemiological and evolutionary benefits. And yeah, there are a cornucopia of possibilities. And so the models allow us to examine the ranges of potential scenarios. And we do so, and we let readers and listeners do so with the online applications. So you hear some acknowledgements and some funding. Thank you very much for listening.
Thank you very much, Chadi. Great, really beautiful talk.
Thanks.
Chadi, what's next?
Great question. So I guess further refining the models, and one can try to incorporate all the data that's coming out into these kinds of models and try to figure out what, narrow down what scenario we're in.
Yeah. One thing, of course, where we've been doing a lot of work with the University of Virginia group is on the weakness of the notion of the herd immunity thresholds and the importance of heterogeneous transmission due to a variety of factors, including spatial factors. So one of the things we've learned in this pandemic is how far off we may be with estimates of, for example, the fraction one needs to get vaccinated. Do you want to say anything about that, Chadi?
I mean, I think Malha would be best to answer this.
I'll be brief. I think, it's first of all, Chen is also here and Max is here. It's really worked with all of us and Marty as well. But I think in short, we see this interesting situation where effectively we have to challenge the commonly held notion of herd immunity thresholds. It simply, to me, as defined in an abstract mathematical form, does not make sense in reality when heterogeneity arises. Now, I don't think so we have a golden bullet to say that herd immunity is really 90% or 80%, because I don't think that concept is very well defined. And hopefully our paper will sort it out in the coming weeks and we can present that. But that's how I think we should think about it, because it's a concept based on mathematical abstraction where you have one single peak. And when that abstraction goes away in heterogeneous systems, you simply don't see that play out. So I had one more thought. I first of all, Chadi, really this brilliant work. You folks have been on a roll here. You, Simon, Jessica, Brian. And I think I like the simplicity of the models. A couple of things we are starting to do, and I wanted to start a discussion. One is, maybe I'll talk about two threads. One that Mugdha had started working on, and hopefully we'll have something to share with you folks at some point, where we were trying to understand your first science paper, which had to do with seasonality, but to look at it when we have a patch model that covers the US rather than just a SIR model for a single region. And it builds on the initial intuition that Cecil and Brian Grenfell had about cities. If you remember that they had these synchronous waves coming in. So we wanted to see what happens with it. As we make a little bit more progress, we'll share it with you folks so that we can have a real robust discussion. The other part that Balthazar has begun leading is, I think it's interesting. So it basically, you can take all your models, but add this extra component of adaptive human behavior.
Yeah.
And I think that's an important one. Simon has always pointed out that it's an important one. So, we have a particular framework, but I think it's a nice way to extend the models where you decide that humans pull back their interactions in an adaptive manner. And we want to see how the results that you had presented here would change when individuals adapt their behavior, which is clearly one of the big factors here. So
that's very interesting.
Yeah. So as soon as we have, we've gotten one paper through, but we want to share this with you folks as soon as, if you folks are ready, then we can chat. I think it will be a very nice extension. It will be one more thread in your series that you have created.
I was going to say that's a really important area that we've been looking at. One example would be how human attitudes towards vaccinations, getting vaccinated depends on the prevalence of the disease in the area. So this is a kind of co-evolutionary model between disease dynamics and individual behavior that can give rise to waves of oscillation. As disease prevalence increases, vaccination rates go up. That drives disease prevalence down, vaccination rates go down, et cetera. So there are all sorts of complexities in there, and we're seeing them in the data as well. So that's great. We're ready to talk to you about that anytime, Madhav.
Right. That will be very good. It fits nicely with the mask wearing stuff. It's the simplest form there, of course.
Right.
The last topic that we all, just got funded for the NSF project with India is the biosurveillance part. And again, Balthazar has built some initial ODE style models, based on the work you folks have done. And then we have also started, Anil and Safat and Andrew have begun work on the network style models. But we want to couple surveillance systems to this issue. If you can detect something sooner, because that's when the adaptation potentially happens, or you might be able to do intervention. How does it affect? How does the strain dynamics evolve in time? So this detection is a central question of our NSF project. So we're just starting, and that's another topic that can really build on very nice sequence you have laid out. I just thought I'll bring this to your notice because I think it provides multiple forms of interactions, and I think you've already laid out the groundwork for doing it.
Connecting what Madhav was talking about, herd immunity part, and also model structures that Chadi presented in the first part. When we think about herd immunity models, one is this heterogeneity in the mixing or like network structures, but in general, what you're showing is like just the immunity profile can be very complex. If you look at it as a population, not everyone's in fully recovered, fully vaccinated, or somewhere in the middle. So if you look at that heterogeneous immune profile that across the population, what does that, can we say something about herd immunity in that kind of a context? We are actually looking at it more in this distribution sense. So if you look at one axis as vaccine protected, is there something that we can generalize that concept of herd immunity by just looking at that overall immune profile? I don't know how best to characterize it, but like that's the kind of question that we're facing right now.
Yeah, certainly you can pose these problems, and I guess with ODE models, you can definitely build very complicated models that keep track a lot of different immune phenotypes, and then derive these conditions. But I think, as we've shown, even with the very simplest case here, with just a few immune phenotypes already, it becomes complicated because you have to pin down what the parameters are, and that's not obvious. So I think it becomes a problem of increasing complexity. So I agree that it's difficult, but I think in principle it can be done if you have the right data set.
Yeah, I think like the complexity that we add by adding heterogeneity is in one direction, the orthogonal direction to adding complexity by this increasing the immune phenotypes.
Exactly.
Yeah, they can complement.
I agree.
Nicely.
Yeah, I agree.
And maybe a quick related question. I don't know if there are thoughts on this. Like basically, all the immune modeling, or like not the vaccine immunity that we're talking about, there is one with respect to infections, which is what you're mainly looking at in this kind of models, like the subsequent
transmission blocking,
the transmission dynamics. Whereas the deeper immunity, which results in preventing severe diseases.
Yeah, so this is so we can consider that too. So we actually do that by assigning that a fraction of them, a fraction of different infection types lead to different number of severe disease. So that can all be. And actually, it's a slider, I think, on the online application. So this can all be determined. So you can say, well, what if this vaccine is poor at, it's got short duration of immunity, and you have high susceptibility to infection after immunity wanes, but you've got very low chance of a severe case. And you can look at all this and these kinds of models. It's the simplest kind of model, but it allows you to probe the different kinds of potential outcomes that you might get. Yeah.
Yeah. The reason I was asking was, I think Madhav can also expand on some of this, because we're part of this scenario modeling hub, which is a collective effort of 8 to 10 modeling teams at this point. And we're modeling different kind of scenario projections. They're still calibrated to the ground truth, but under different assumptions of waning immunity and then partial protection against severe outcomes. And then under those conditions, evaluating what is the impact of, say, rolling out boosters, and what is the impact of expanding the vaccinations for children. And so there is one approach where we are actually calibrating to the ground truth and then looking at percentage changes in the future course, which is how we are taking, we are doing scenario-based projections from current. But I think these mathematical models can give us a much more richer view. Not just calibrating to the current point, but what are all the complex interplays of these. I think that's a useful view to add to that discussion. yeah, so that's just a thought. Yeah.
Yeah, thanks. Yeah, no, I agree. It's very interesting.
Right. I think, Chadi, to follow up on what Srini said, the Scenario Hub is currently discussing possibly next set of scenarios to work on. And I think maybe that's what Srini is alluding to, that perhaps the work you have done could form the basis of the next scenario. So this happens every month. Cecile actually runs this, one of the people with Kat at Penn State, and Rebecca and others. But the point being that maybe this work could be one of the scenarios, and there are multiple modeling groups that come together. And Srini, am I catching the basic?
I think that's part of it. The other thing that I was thinking was just in general, like when we look at what is the marginal impact of childhood vaccinations, the way we are looking at it in the Scenario Hub right now is all these models calibrate to the current, and then under different scenario assumptions, try to layer in vaccination and see, like, quantitatively say, okay, it's going to be 20% under higher waning and then 15% under lower waning, or something like that. Like they come up with this quantitative projections. But I think just understanding this complexity of this modeling landscape and then saying, depending upon which regime we are in, it might be more or less. And then the question becomes more of estimating which regime we are following right now. So rather than the current approach of like fitting and projecting forward, it's more of understanding the landscape of the model and then saying, okay, we're more likely in this regime A versus regime B. And so we might see more impact of childhood vaccinations versus less. I don't know if that makes sense. Like basically flipping the question of projections to more of a estimating state once we understand what the implications of the model are.
Right. I think that makes sense as well. Yeah.
But in answer to your suggestion, Madhav, in terms of the next scenarios, we'd love to collaborate on that if that's a possibility.
Right. I think we could, we can tell Cecile that if you could present some of the work there in that meeting, if they are allowing presentations, and then, or at least say, they're asking for suggestions on scenarios. So maybe we can have a short meeting and say, this is the scenario that we have come up in discussions with the Princeton group. And then everybody, sort of votes on it. It's a sort of semi-democratic way of doing it, which is good. So then part of it depends, of course, believe it or not, on the ability of the modelers to do that. So sometimes they will take up a scenario because they think it's tractable. Other one, they won't. So I think it's a really good idea. The policymakers get to see it. That's the best part. So
I think that'd be great. I hope Chadi agrees.
Yeah. Okay.
If there aren't any more questions, then we can wrap up for today. Just want to say thank you again to Chadi and Simon for great talk and discussion after. And we'll be back here in 2 weeks with a talk from Maya Majumdar from Harvard University. So I hope everybody can attend.
Thank you very much for having me.
Thank you very much. Brilliant talk again. Great work.
Thank you.
Yeah.
Thank you.